we want to evaluate the given double integral over the region D, where D is defined here, where D equals a region where x squared plus y squared is less than or equal to 1 and x is greater than or equal to 0. So we should recognize that x squared plus y squared equals 1 would be this circle in the xy plane. So for this first inequality, x squared plus y squared is less than or equal to 1, we'd have the circle and all the area inside, but notice how x also has to be greater than or equal to 0, which would be just this half circle here. So this is the region of integration, and because the region of integration is a semicircle or half circle, we're going to write the double integral in rectangular form as a double integral in polar form. To do this, remember, we need to write f of x comma y as f of r comma theta. To do this, we substitute r cosine theta for x and r sine theta for y, and the differential a is equal to r dr d theta. Before we do this, though, let's look at this graphically. The integrand function f of x comma y is graphed in blue. If we look down on the xy plane, we can see the region of integration would be this semicircle here. Notice how in this pie-shaped area in the xy plane, the integrand function is below the xy plane, which means in this case the double integral does not represent the volume bounded by the surface in the xy plane over the region in the xy plane. We can still evaluate the double integral, just remember in this case it does not represent volume. So to get started, notice that f of x comma y is equal to 4x plus 3y, which means f of r comma theta is going to be equal to 4 times x equals r cosine theta plus 3 times y, where y is r sine theta. So our double integral in polar form is going to be, again, f of r comma theta times r dr d theta. So we would have 4r cosine theta plus 3r sine theta times r dr d theta. Now let's find the limits of integration for r and theta that would trace out this area in the xy plane. So notice how the radius r would be from 0 to 1. And then to trace out this area, we would have to start here at negative pi over 2 radians, and then rotate counterclockwise to here, which is pi over 2 radians. So the limits of integration for theta are from negative pi over 2 to positive pi over 2. Notice how in this sum here we have a common factor of r. Let's factor out the r and write this as r squared. So our integrand function would be 4 cosine theta plus 3 sine theta times r squared dr d theta. And now let's go and evaluate this on the next slide. And now we integrate with respect to r, treating theta as a constant. So we're going to have this sum times r cubed divided by 3, which we can also write as 1/3 r cubed. So we substitute 1 for r, then 0 for r, then find the difference. So we'd have 1/3 times 1 cubed minus 1/3 times 0 cubed. Notice how this just simplifies to 1/3. Let's go ahead and write this as 1/3 times the integral from negative pi over 2 to positive pi over 2 of 4 cosine theta plus 3 sine theta. And now we integrate with respect to theta. So 1/3 times the antiderivative of 4 cosine theta would be 4 sine theta plus the antiderivative of 3 sine theta would be 3 times negative cosine theta, or minus 3 cosine theta. So we have 1/3 times, when theta is pi over 2, we have 4 times sine pi over 2 minus 3 cosine pi over 2. So all this is when theta equals pi over 2, and then we have minus, when theta is negative pi over 2, we have 4 times sine negative pi over 2 minus 3 times cosine negative pi over 2. So we end up with 1/3 times sine pi over 2 is equal to 1. So we have 4 times 1 minus cosine pi over 2 is equal to 0. So we have 3 times 0 minus 4 sine negative pi over 2 is equal to -1. So we have 4 times -1 minus 3 times cosine negative pi over 2, again, is equal to 0. So inside the brackets we have 4 minus -4, which is 8. 1/3 times 8 is equal to 8/3. And this is the value of our double integral. I hope you found this helpful.